to 0. Cosine square of x has a singularity at x is equal to pi over 2. And I don't know whether you teach Fuchsian differential equation, probably not in undergraduate. But yeah, just this, it's called, it has a regular singularity at x is equal to 0, and this g, it has so-called characteristic exponent at x is equal to 0, that is g and 1 minus g. And at x is equal to pi over 2, it has a characteristic exponent at 1 h and 1 minus h. And when you look at this, just forget about the constant part. This potential is definitely invariant when you change g to 1 minus g, or 1 minus g to g, h to 1 minus h. But these, this is a symmetry of the potential, but it is not the symmetry of the eigenfunction, right? When you change g to 1 minus g and g is greater than 1, this, for example, sine x of 1 minus g is no longer square integrable at x is equal to 0. So this is not, the eigenfunctions are not symmetric under this transformation. That is because the eigenfunctions are required to be square integrable. The ordinary solutions, when it is 0 here, it might be going to infinity at the other end, and etc., etc. So in order to make eigenfunctions, you have to throw away unwanted solutions. Therefore, its eigenfunctions do not have symmetry, but the potential itself has this symmetry. Then, when you apply this discrete symmetry transformation to the eigenfunction, it will give you definitely a solution, but no longer eigenfunction. It will not be square integral. So just by doing g to 1 minus g or h to 1 minus h, you can get a seed solution with for certain degree. Then you can choose the energy to be negative, and these are not square integrable, and its inverse is again not square integrable because its one part vanishes, but the other part goes to infinity. So inverse is that on this end it becomes square integrable, but on this end it's infinite. So it's like this. But when you check, you can show that they have no zeros in between. So the idea is that you can use all these seed solutions, m or m plus n seed solutions. Then, here explicit form of the seed solutions. Just here in h to 1 minus h, you get this. Then the polynomial type is just changed g 1 minus a, not g, h 1 minus h. Then you can calculate its energy. Then it will be like this. So if the degree is less than h minus 1/2, this is definitely negative. And when you do the same thing, g to 1 minus g, the energy is this. So if v is less than g minus 1/2, the energy is negative. And you can also verify they have no zeros in between. What else? Okay. So this is the idea of the Dalbu transformation. You have original eigenfunctions with the degree 0, 1, 2, 3, and the seed solutions are of negative energy, so they are below this. So you use seed solution, one of the seed solutions, D1, and the other D2, etc., m times. Then you come to this new eigensystems. And remember, this is just applying A and A dagger. And since A and A dagger used by these low seed solutions, they will not annihilate any eigenstate. So these transformations are so-called exactly isospectral. You remember, the eigenvalues are not changed. The eigenvalues of these each the same here. So this is just, I wrote down the new Hamiltonian has a new eigenfunctions that is just obtained by using these seed solutions, and Wronskian here. And these are the norms, and these norms are always positive. And this new Hamiltonian are just potential are just obtained from the old potential by just taking logarithmic derivative of the Wronskian of the denominator, second derivative times 2. So these are exactly solvable, and the eigenfunctions are given there. And here is so when you calculate these eigenfunctions, just calculate, then this you can divide them into the orthogonality wave function times the polynomial. And this important thing is that this polynomial at degree 0 is almost the same as the polynomial appearing in the denominator. So when you just look at this as this is almost the same as the old ground state wave function. Just the parameters are changed slightly. So when you look at this, then the new eigenfunctions are just a polynomial degree L plus n polynomial divided by degree L polynomial. So you might wonder, or everybody has wondered, this, if this starts at degree L, the constant, how you can express the constant. And then for that solution, the lowest order polynomial divided by this is almost a constant. Therefore, you can understand this. This is not violating the completeness. You can also show that its orthogonality is satisfied. And this is just explicit forms. All these polynomials can be original here muse using original polynomials times certain factor, original polynomial. Here you change original polynomial to h to 1 minus h. Here you change original polynomial g to 1 minus g. And these you just put things here. And this is the polynomial in the coming denominator, almost the same thing. And you can, since these are just Wronskians of the polynomials, you can easily know the degrees. That degrees are the sum of the degrees of the original seed functions, and certain combinatorial factors must be subtracted. This is always greater than 1. But since these are rather general, so this much is done, proved. But in order to give you some feeling, how things, I'm going to show you how things look like in the simplest one. So the original Poisson-Teller is just sine square of x, cosine square of x. So their starting point is that this plus some additional thing, 1 over cosine 2x and 1 over cosine 2x squared. So this is the form, well, slightly different notation where Kim wrote down in 2008. And I just looked at this formula for about 10 months. Then I realized, well, as I told you, this any potential can be uniquely expressed by its ground state eigenfunction. So I just wrote down the ground state eigenfunction of this. It is sine square of x times g plus 1, since it is changed to g minus 1 to g. Cosine of x times h plus 1 times ground state is just the degree 1 polynomial of this and this. And it took me about 10 months to realize that this denominator is just a Jacobi polynomial with just shifted, so h changed to 1 minus h or something. So g, instead of g minus 1/2, it's g plus 1 2/3, g minus g minus 1. And the numerator is just g is increased by 1, h is increased by 1. So when I just noticed that, then it was very easy for me to generalize to degree L. You just have to, so this W is the log of this. So instead of g plus 1, you make it g plus L and h plus L, and here instead of g plus 1, you make it the Jacobi polynomial g plus L and h minus L, and use this. So you just introduce the certain singular potential that is not this, but depending on this cosine. And this, when you look at this, cosine x goes between minus 1 to 1. So when you look at this, and think a little bit, you will know this will not, this has no zero in between minus 1 and 1. So these are the idea, just how I came to think of this. And the thing I explained is the one I later formulated with the language of the Dalbu transformation and the seed solution. The idea is that the seed solutions are obtained by using discrete symmetry transformation. And you can also prove so-called shape invariance. I didn't have time to explain this, so you just can forget about that. Eigenvalues you can easily calculate, just changing g to g plus L. And eigenfunctions, for example, just you can write down also explicitly. And from this is degree n, and this is degree L. So this is degree L plus n polynomial. And as I told you, that lowest degree polynomial is just a denominator polynomial with parameter slightly shifted. So it's almost, lowest degree is almost constant, and the orthogonality. And you can also write down the Schrödinger, the differential equation for these new polynomials. If you forget about this, if you make C is equal to 0, this is just a differential equation satisfied by the ordinary Jacobi polynomial. But you have this and this, so at the 0 of this polynomial, this is singular. So this singularity you can easily calculate at the 0 of this. So you just write down the most singular part, saying this eta j, and from this you can calculate so-called characteristic exponent. And this is this second derivative. So the idea is that you look for the solutions y that is written x minus eta minus eta j to the power rho. And then such solutions, when you make the second derivative, it's this eta minus eta j times power rho and rho minus 1. And here it's just a degree to, again, rho power rho. So the solution must be satisfied this. And rho is equal to 0, corresponds to the polynomial solution. So this is almost the end of my talk, but you might wonder why. There are so many clever experts in working in orthogonal polynomials. Why these new polynomials were not discovered by the experts of the orthogonal polynomials? So the answers are that the physical thinking, so physicist thinking maybe is more suitable for this kind of problem, because the Schrödinger equation is more general than the ordinary second order differential equation for the polynomials. And again, the second point, I could get these seed polar solutions by using the discrete symmetry, G to 1 minus G, H to 1 minus H. But as again, I emphasized, these are not the symmetries of the Jacobi polynomial or Ragel polynomial equations, because the equations for the Jacobi are the equation for the eigenfunctions. So one solution removed, so it's no longer have such symmetry. Yeah, these are eigen solutions of eigen polynomials. So these are non-square integrals. So when you concentrate on the equations of these polynomials, then you do not see such symmetries. So it's not so easy to deform them. And again, the Dalbout transformations are defined most generally for these Schrödinger equations, not for the hypergeometric equations or Jacobi polynomial equations. So these are about the contents of the recent discovery of exactly solvable quantum mechanics. But again, as I told you, that the concept of quantum mechanics can also be exported to the difference equations. And as I told you before, this in a way, the Heisenberg thought about that. You could also consider quantum mechanics in terms of difference Schrödinger equations. And since I don't have time to explain all these things, but essentially the same thing can be done for difference Schrödinger equations that would produce Wilson polynomials, ASCII-Wilson polynomials, LeCosPA polynomials, Q-LeCosPA polynomials. You can also discuss you can also generalize the concept of Dalbout transformations for these difference quantum mechanics, difference Schrödinger equation. And you can also discuss the discrete symmetries of the Schrödinger equation governing Wilson or ASCII-Wilson or the other polynomials. So all the ingredients are there. So you can also produce new orthogonal polynomials based on ASCII Wilson polynomial. These I have done with my colleague Odake-san for maybe 2-3 years ago. And you learn that these orthogonal polynomials appear in many parts of mathematics and also physics. For example, representation of various groups, because special functions are always related to such things. And these deformed orthogonal polynomials can always be, so you can also consider the formation of such subject, harmonic analysis or whatever, the representation theory or any geometry, etc. So there will be, wherever orthogonal polynomials appear in physics or in mathematics, you can also discuss their deformation by using these orthogonal polynomials. And yeah, I just wrote down the exactly solvable Grothendieck processes, but that's again, it takes time to explain these, so I will omit it. And I want to emphasize that the various concepts and methods of quantum mechanics has much wider currency and utility in the theory of ordinary differential and difference equations. So in that sense, I think physicists are more, in a better place compared to the experts working in the so-called classical analysis, because we have a much more general framework and also explicit examples for thinking explicitly. And this I want to emphasize to my younger colleagues, that the learning quantum mechanics quite seriously, I think, has always quite good, will give you good rewards. And the third part is maybe for mathematicians, it's various properties of known things, ASCII scheme of hypergeometric orthogonal polynomials. So you can construct a better unified theory from physicist point of view in a quite nice way. And this is, I told you that one-dimensional quantum mechanics with difference and differential equations, you can do this. But I haven't yet done, since I'm already retired. The nice thing is that for quantum mechanics, you can also consider multi-degrees of freedom quantum mechanics. And they are so-called Calogero-Moser systems. And it's different, its eigenfunctions also, these Jack polynomials, etc. And also it's a difference version, the so-called Rice-Nash-Snyder system, and its eigenfunction, the also known polynomials. And I think you can also consider the formations of such multi-degrees of freedom quantum mechanics. And if you are lucky and clever, you might be able to construct multivariable, multi-indexed orthogonal polynomial. This is about what I wanted to say. Thank you very much. Yeah, 5 minutes or so for, I just left for discussion.
So, the question, anyone?
Yes, please.
Using this technique, is it essential that Hamiltonian is written in AAA? Is it essential?
I didn't say it's essential. It is always, any quantum mechanical Hamiltonian can be written AAA.
There is another area called two-dimensional solvable systems, and there is a notion of infinite dimensional the algebra. But
Yeah.
there is something similar in this area.
They also have intertwining relations, yeah, etc., etc. Yeah, I think so. Yeah. Yes.
So people also consider wave functions with internal space, like a column of wave functions as a
So
generalization.
the system with spin or
Right.
finite dimensional, I think it's possible because the basic wave functions are usually this kind of thing, but the details I have never. So maybe this is a good problem for your good student. I didn't think, yeah. And also the question that can we do this for Dirac equations or others? So any established quite well exactly solvable system, considering its deformation is quite challenging. Yeah. Well, just when you consider a deformation of classical mechanics, you just got quantum mechanics, right? this kind of, so this is of course a much smaller scale, but you can consider the many different deformations and many interesting things could be done.
Okay.
Yes.
So, do you know any potential that exactly solvable potential can help us understand more on some systems such as molecular dynamics or something like that, like condensed matter or something?
Oh yeah, this partial telepotential, I think, was invented or discovered in the 1930s in connection with some molecular interactions. So all these, I think, with some relationship of course, for example, the Coulomb, right? Thing 1 over x potential plus x, 1 over x squared plus some more. We can also deform Coulomb. I didn't have time to say about Coulomb, but that can be done also.
Any more questions? Okay, if not, let's thank Professor Sasaki again for a very interesting talk.